Welcome back. We want to continue with the revolution of the Earth around the Sun. The Earth, while rotating once every day, as we now know, revolves around the Sun once every 365.256 days. You should keep in mind that this means we move around the Sun at a rate of about 1 degree per day. This is known as one sidereal year, sidereal meaning in relation to the stars. So the length of the orbit is measured in relation to our return to the same stellar reference point 1 year later. So you pick a star, you go around 1 year, come back to that star, and that takes 365.256 days. And because there's this extra quarter of a day and change, every 4 years we have a leap year. And because it's not exactly 0.256 days, we have to then cancel leap years every 100 years and then add the leap year back in every millennium. So for people like me who lived through the change of millennium, 1999 to 2000, we had a leap year, while people who lived from the century change of 1899 to 1900 did not have a leap year in that year, 1900. So, fun facts. The Earth orbits the Sun at an average acceleration of 108,000 kilometers per hour, or 30 kilometers per second, and again, acceleration as it's moving on a curved path. Oh, we want to actually blow this up, don't we? Sorry. So, that's easier to see now. Sorry about that. The Earth revolves around, again, the Sun on an imaginary plane called the plane of the ecliptic, and it's tilted at an angle of 23.5 degrees. Our Earth on its rotational axis. We call this similarity of our rotational axis parallelism, the fact that it's always pointing in the same direction day after day after day after day. This would be an illustration of that, with the red portion of the axis pointing towards the celestial North Pole, and the green part of the axis pointing towards the southern celestial pole. Again, we are lucky in our era to have Polaris, a star, near our celestial North Pole, whereas in the southern hemisphere there is no object, but there is a constellation that can be used to locate an approximate point, the Southern Cross. The shape of the Earth's orbit is an ellipse. This is a new word. You need to know this word. An ellipse is a slightly flattened circle. And elliptical orbits trace a path that, again, looks somewhat flattened compared to a perfectly circular orbit. And another aspect of this elliptical orbit is that the center of gravity is off-center. So rather than the center of gravity being in the very center of a perfectly circular orbit, the gravity is a little bit off-center, and we can see that in this diagram. So here we would have the Sun slightly off-center in this ellipse, and the point at which the Sun is, the point that the Sun is occupying is called a focus. Every ellipse has two foci. In our case, in our solar system, one of the foci is empty. The other has the Sun located at it. This also leads to the fact that at some time during the year, in January, we reach a point called perihelion, January 3rd, today, where we're closest to the Sun. And that a half a year later, we reach a point on July 4th called aphelion, where we are furthest from the Sun. So this is something to remember. As the year goes by, we change our distance. Of course, we change our distance because we're in elliptical orbit. That has consequences then for the rate at which the Earth travels around the Sun, because at some points we are closer, therefore there's more gravitational attraction, and we're moving quicker. And at some points that we are further, therefore there is less gravitational attraction, and we are moving more slowly around the Sun. Again, the Earth reaches perihelion, the moment when it's close to the Sun, in its elliptical orbit on or near January 3rd, today. So you should make sure you know this. The Earth reaches aphelion the moment when it is furthest from the Sun on or near July 4th.
prefix peri is from the ancient Greek, meaning at or near, and the prefix ap from the ancient Greek apo, meaning away, far off. Another piece of evidence for the revolution of the Earth around the sun is suggested by the change in stellar constellations over the course of the year that one can see. So if one is looking out in January at midnight, that would be on this far side of this gray sphere, as opposed to on the inside where it would be solar noon. Midnight looking out, you would see Cancer. But a half year later, at midnight looking out in, say, July, you would be seeing Capricorn. And this change over the course of the year is evidence that the Earth is revolving around the sun. The Earth does not move at a constant speed. We mentioned that, and that is because of the Earth's elliptical orbit and its axial tilt. That is its obliquity. That is the fact that that tilt varies over the course of the year. And that change in axial tilt has a slight impact on our acceleration around the sun. The variation can be easily observed by timing the arrival of solar noon over the course of a year. And we did this when we went up to, or we learned about this briefly when we went up to the sundial and showed you, made a little video of that. The variation between clock time and sundial time, or solar time. And again, the equation of time is not an actual equation, but a series of observations of the Earth's speed and its variation from an average that you would find on a watch or a clock. It was only really discovered once people had accurate clocks, and it came to the attention of people once they were able to compare accurate clocks to the time they were seeing on a sundial. Here is a lovely little illustration of how eccentricity in brown changing over the course of the year. In other words, how sometimes we're further and closer to the sun, changing at the rate at which we move around the sun, can be combined with the change in our axial tilt over the course of the year to give us a difference between a clock and the sundial at any given point of the year. And we are now in this period of early January where we're moving a little bit faster. The clock is going ahead of the sun. If you recall, back in November, we were moving at a difference of about 13 minutes as opposed to now. Pause for one moment while I get the cat out of the room. Back. Sorry about that. And one of the beautiful things that has fallen out of people's observation of the sun in the sky over the course of the year as we revolve around it is that there's this beautiful shape called an analemma that the sun forms if you take a picture of the sun every day at exactly the same time from the same position. This analemma shows how the sun follows a path where in the winter, moving more quickly, it covers more distance apparent through the sky than in the summer near the solstice when it is further away and covers less distance in the same amount of time. This diagram also is able to help you find the sun's subsolar point or zenith angle on any given day. You look at the latitudes, or what are called declination of the sun, and you find that if you pick a date, for instance, let's pick April, is this right? We're going February, March, let's say March 5th. We just go over to here, and we find that the subsolar point on March 5th would be approximately 5 degrees north latitude. You just pick a point and go over to the axis, and then down on the x-axis up here, it's showing you how much faster or slower the sun appears in relation to the clock. And right now the sun is slower than our watches. As we then remember, back in November, the sun
was faster by about 13 minutes on the day we were out there, which was about November 20 something. And here's what I was trying to describe as what a human can actually see by setting a camera up and taking a picture of the sun on consecutive, well, not consecutive days, but on a series of days over a course of a year. As long as you don't move that camera and keep coming back and just taking pictures at exactly the same time. So this was done in Hong Kong, 7:30 a.m., and you can see in the summertime, when the sun and the earth are at maximum distance apart, the distance traveled by the earth in relation to the sun is less in the same amount of time as here in the winter. And then this variation in where the sun is located in the sky, either from spring to fall, in any given year, is due to the axial tilt, the change in the axial tilt as it moves away and then moves back. And here, if we just, well, we'll skip that. Okay. The combination of the Earth's 23.5 degree axial tilt and its revolution around the sun causes changes in the Earth's seasons. This is critical. The combination of the Earth's 23.5 degree axial tilt and its revolution around the sun causes change in the Earth's seasons. This is why we have seasons. If we had no axial tilt, we would have no seasons. If we had less of an axial tilt, we would have less extremes between each season. And if we had more of an axial tilt, we would have greater extremes between seasons. The changes as we know them now are marked by two solstices, the winter and summer, on or around December 21st for winter and June 21st for summer. Two equinoxes, vernal spring and autumnal fall, on or around March 21st and on or around September 21st. Here we see a diagram that we've looked at once before, which shows you how the Earth's tilt causes the Earth to be warmer in the northern hemisphere with more daylight in the summer as we tilt towards the sun, and colder in the northern hemisphere in the winter as we tilt away. Total darkness in the Arctic in the winter, total daylight in the summer. And here at the equinoxes, we have the Earth's axial tilt at a right angle to the sun, splitting the Earth perfectly in half through the poles, 12 hours of daylight, 12 hours of night. The seasons are cyclic and predictable. The seasons are cyclic and predictable. That is what you must know. As the Earth revolves around the sun on an elliptical orbit, what causes the changes of the seasons? It's an easy answer. The Earth's axis of rotation tilted. I said this time 23.4. There's a range, okay? I was taught 23.5, but it's changing. And so 23.4 is actually probably a little bit more accurate. Here is a diagram that shows how the Earth's changing tilt causes the seasons because the angle at which the sun strikes the Earth is at low angle in the winter in the northern hemisphere and high angle in the summer in the northern hemisphere. And so this change in the angle at which the sun strikes the Earth is what causes the seasons to vary as we tilt either away from the sun in the winter or towards the sun in the summer, and have a balance with the hottest part of the Earth being in the equatorial region in the spring and fall, and therefore the balance between northern and southern hemisphere, or a kind of equality in terms of the amount of sunlight being received. And we can look at this in a simple way by looking at the sun striking the Earth at noon at the equinox at the equator. And if you look, you would see that 1 kilowatt of energy from the sun strikes 1 meter squared. Now, if we went to the sun striking the Earth at New York City at noon on the winter solstice, which is at about a 25 degree angle, you would see that that 1 meter has increased to 2 meters squared, but the same amount of energy is striking it. Therefore, the temperature cannot increase as much in the winter on the ground as it can in New York City, as it can at the equator when the sun strikes the equator on the equinoxes at
that location's zenith. And that location becomes the subsolar point on the Earth. The angle of the sun's incoming solar radiation determines the amount of heat absorbed by the Earth. Incoming solar radiation becomes a beautiful new word called insolation. So when I say the amount of insolation, I mean the amount of incoming solar radiation striking the Earth in a given area. In this case, the amount of insolation is 1 kilowatt per meter squared. In this case, it's 1 kilowatt per meter, 2 meters squared. So we need to know how much sunlight is striking the Earth. We call that amount the insolation. Latitude then becomes very important in terms of how warm or cold the Earth is. It affects the amount of insolation received at the Earth's surface. The subsolar point, the point on the Earth at right angles to the plane of the ecliptic, and insolation receives the most of the sun's energy. Insolation decreases north and south of the tropics, which is where in the northern hemisphere at the Tropic of Cancer you receive the sun at your zenith at its maximum to the north, and then again in the southern hemisphere at the Tropic of Capricorn. So the subsolar point at a right angle can be only found between the two tropics, 23.5 degrees north and 23.5 degrees south. Everywhere in here we can have a subsolar point of 90 degrees over the course of the year. And in some of these areas you get it twice. So the equator gets it twice, spring and fall. Everywhere else gets it twice, but then at the tropics only once. This then creates latitudinal zones in terms of the way in which we think about parts of the Earth. We have an equatorial and tropical region that we should be aware of. We have a subtropical region from 23.5 north to 35 north. Our region of the Earth is considered the mid-latitudes from 35 degrees north to 55 north. The same would be in the south, southern hemisphere, subarctic, and Arctic. These are your latitudinal zones as defined by geographers. Subsolar point in the tropics receives at any one of those given subsolar points 2.5 times more energy than is being received at the poles. So the tropics are the warmest part of the Earth. The circle of illumination is simply a moving border that separates night from day as the Earth rotates into the sun each day. So as we rotate into sunset tomorrow, we will enter the circle of illumination, the circle of light, and we will be there for some 9 hours, and then the sun will set. And over the course of the entire Earth, every single person enters or leaves that circle of illumination this time of year, with the exception of people up north of 66.5 degrees north who are in total darkness. The final point here is that the winter solstice in the northern hemisphere always has the sun rising south of east and setting south of west, with about 9 hours of sunlight in New York City. And I mention this because it's just to remind ourselves where the sun is for us here in the northern hemisphere. And again, at solar noon, at the meridian, the sun will always be in the southern sky. At the summer solstice, we have the sun rising and setting north of east and west, and we have about 15 hours of sunlight. And at the equinoxes, 12 hours of sunlight, with the sun rising in the east and setting in the west. Now again, why is this really important to remind ourselves of? Because half the Earth experiences this in a different way. In the southern hemisphere, winter solstice has the sun rising north of east and setting north of west, because the sun at solar noon on the meridian is in the northern sky. You are looking up from the bottom, as it were, as we have defined it in the northern hemisphere. You are looking up from the bottom of the Earth. So the sun is in the north, whereas we look down towards the south. So then we can continue by saying the summer solstice, we have the sun rising south of east in the southern hemisphere and setting south of west, the opposite of our northern hemisphere.
The equinoxes, it's the same. Again, this would be a diagram of your southern hemisphere solar paths. Summer, equinox, winter, solstice, with the sun hitting the meridian in the northern sky, as opposed to us in the northern hemisphere. Path of the sun, path of the sun, path of the sun at the solstices and equinox, with the sun striking the meridian, passing through the meridian, culminating in the southern sky. And with that, we will call it complete.